Hello everyone, so today I'm going to speak about AUV navigation using Isobath. This presentation is part of MOQESM 2020, which is a conference held inside the CTech Week 2020. So I'll start with a little bit of introduction and context. So nowadays we use AUVs because of the increasing need for data in the maritime environment. Also the development of underwater sensor fields forced the development of AUVs because we use them as data mules to transport data from one node to the other, or to get the data from the sensor field to the surface. And also we use AUVs in underwater mining context. We use it for monitoring the area we are mining to make sure that everything is running smoothly. So this presentation is supported by Kopadia, which is a company specialized in maritime mechanical engineering, underwater inspection, and underwater engineering solution design. The objective now is to develop a low-cost, easy-to-operate modular AUV named the Folaga, based on the Folaga developed by Graaltech, but it has been modified with thrusters, two thrusters at the back and thrusters here and here to move round and to go up and down, and with a new algorithm to operate. So I'll speak a little about AUV navigation and localization methods. First, there is inertial navigation. Here we use an IMU to measure the rotational acceleration and the acceleration of the vehicle, and then we integrate those measurements to get the speed and then the position of the robot. But because of this integration, there is a phenomenon called drift that appears, and so the longer the mission is, the bigger the uncertainty will be. So sometimes to help with that, we use for example, a DVL, and with a bit of sensor fusion, with a measurement of the DVL, we get a better approximation of the position of the robot. There is also acoustic methods like long baseline localization and ultra-short baseline localization. The first one works with several beacons. So they are either fixed on the seafloor or attached to buoys on the surface. The beacons have their absolute position, and they transmit message to the AUV, and the AUV will be able to triangulate its position relatively to the beacons, and because the beacons send their absolute position, it will be able to know its absolute position. And then there is the ultra-short baseline localization methods. Here the AUV itself doesn't know its position, but thanks to hydrophone attached to the surface vehicle, the surface vehicle will be able to listen to the AUV to know its absolute position. And then there is terrain-based navigation methods. Here the robot has a prior map of the area it has to investigate embedded, and it will do some measurements, and it will compare these measurements to the map it has to know its position. And the longer the mission is, the better the positioning will be, because as it has the previous knowledge of the different position it had, it has more constraints for the calculation of the current position. Now we'll speak about Isobath tracking. So it's kind of a terrain-based navigation technique because it uses singularities of the environment to localize the robot. But unlike the TBN method, everything is relative. So here we will use an Isobath, which is an imaginary line where the water column line stays the same. So here on this map we've got one isobath. So on this line the height of the water column is 10 meters, or the seafloor stays at 10 meters depth if you prefer. And we will follow this line and localize the AUV relatively to this line. So how to follow an isobath? For this we need some hardware. So first a pressure sensor to measure the depth of the vehicle, then an altimeter to measure the altitude of the ground of the vehicle, and thus we've got the height of the water column, and we're able to measure on which isobath we are. The advantages of those two sensors is that they are really easy to find, they are cheap, and they're easy to use. So to formalize our problem, we'll use a simple model for the robot, x, y, z, psi. X and y the position in the horizontal plane, and z the depth of the robot, and psi its yaw. And here you've got the state equation of the robot. And we introduce h of xy, which is the height of the water column at a given position in the plane. And thanks to its sensors, the robot is able to observe some things. So first y1, which is the altitude of the robot over ground, which is depth minus water column height. We also have the gradients of the water column height and the yaw of the robot, and we can have the angle between those two, and then the robot depth. And we need to find a condition that would ensure that we are staying on the isobath we want. And for this, we need to keep the yaw of the robot perpendicular to the gradient of the height of the water column measured. Because here, if we stay on this line, which is one isobath at 9 meters depth, the water column line height stays the same along this line. And so the gradient will be always perpendicular to it. So if we want to follow this line, we have to make sure that the yaw of the robot at one place stays perpendicular to the gradient of the water column height. So from our model, the controller should affect the depth of the AUV and the yaw of the vehicle. For the depth, we will only use simple proportional control. For the yaw of the vehicle, we need to satisfy two conditions. So make sure that the yaw of the vehicle stays perpendicular to the gradient of the water column height. So it gives us 1 hour E2, E1, which is Y2 minus pi over 2 or plus pi over 2. This will change if we are going one way or the other way around. And we have to make sure that this error E1 stays as close to 0 as possible. And then the isobath we are following must be the one we want. We don't want the isobath at 8 meters depth or at 10 meters depth, but at 9. So we have to make sure that this error E2 stays as close to 0 as possible. And the final command combining these two aspects is U2 equal to hyperbolic tangent of E1 and plus sawtooth of E2. So you may have noticed that we have no equipment to measure Y2, which is the angle between the yaw of the robot and the gradient of the water column height. So we need to estimate it. And for this, we will use a Kalman filter as an observer to estimate Y2. So in the robot frame, we assume that there is a local plane underneath the robot on the seabed that satisfies the following equation. where P1 and P2 represent the gradient of the plane in the robot frame, and P3 the water column height. And the Kalman filter will return an estimation P hat of P. If you want more details about this Kalman filter, I advise you to read the paper of Luc Jolin made for ISRC 2018. With this new estimation of Y2, the controller is modified slightly. So we still have U1 for the control of the depth, and here for the control of the yaw we've got H0 minus P hat 3, and Y2 is replaced here by the arctangent of P hat 2 and P hat 1. So we tested this controller in a simulation environment, and we had promising results. First, for the depth control, so here we've got the start of the mission. The robot goes slowly to 2 meters depth, which is the depth we want for the vehicle, and it stays at this depth for the rest of the mission. And then for the control of the yaw, we can notice that we are doing a stable cycle. So we try to stay on the Isobath at 9 meters depth, showed here in green or here. And so the robot starts at on the Isobath at 8 meters depth, and then it slowly goes over 8.5 and then reach the Isobath at 9 meters depth, and then it's doing a stable cycle following this Isobath. So this controller is validated at least in simulation. And so we decided to do tests in real life environment. To do so, we run tests at the Lac de Guerre-les-Dents with students at ENSTA-Bretagne. So we've done it 2 scholar years in a row. The first group had to choose the mount the different sensors we needed, the different hardware we needed, and they had to implement the first version of the Kalman filter. It was working, but it was not really stable. And so the second group tuned the Kalman filter precisely for the vehicle they were using. And they were able to go back and forth on the Isobath, following it one way for 10 minutes and going back for 10 minutes. So here are the results made by the second group. So the robot is at its starting and final position. In green is depicted the path of the robot when it's going away, and in red is depicted its path on its way back. In orange we have the horizontal plan at 10 meters depth, because we want to follow the Isobath at 10 meters depth. And in white is depicted the depth evolution of the lake. And we can see that there is a sharp turn here and a sharp turn here when it's going quite straight at the beginning. And these sharp turns correspond to these 2 spikes here. So here are the measurements of the depth made by the robot during the mission. And here we've got measurements that are not not at 10 meters depth, so not on the Isobath. Here also not at 10 meters depth, so not on the Isobath. And we see that those 2 spikes corresponds to those 2 sharp turns. And it's because it's here at this position, it's really going deeper, really the altitude is dropping dramatically here, so it has to turn to stay on the Isobath. So here we've got the spike, and then it goes back on the Isobath, and when it's turning around we've got this straight line, and then when it's turning, it's going deeper this way, so it has to do a sharp turn again to stay on the Isobath, and it corresponds to this spike. And we can see that we have the same if we are going away from the starting position, or if we're going back to the starting position. So now that our proof of concept is done, we want to go further. So we're moving to phase 2. We want to navigate on an Isobath for a longer period. So here it was only 10 minutes one way, 10 minutes the other way. So we would like to make sure that we are able to follow an Isobath for like an hour or 2 hours. We want to be able to execute stable cycles using several Isobaths. So here I'm using the shape of Girledon Lake, which is kind of like a corridor where it's where the deepest point is at the middle of the corridor. So the idea is to follow the Isobath at 10 meters depth, for example, then turn 90 degrees, go straight to go on the other side of the corridor, which is at 10 meters depth, follow the Isobath for 10 minutes, for example, go back, turn 90 degrees, and then go back on the other Isobath and try to find a way to make a stable circle. There is also another idea, which is to stay on a finite part of the Isobath. For example, here we want to stay between A and B and go back and forth between A and B. We've developed a new algorithm and run a simulation. So here in red is depicted the Isobath when it thinks that it's going from B to A, and in cyan the part where the robot thinks that it's going from A to B, and in yellow the part where the robot is not following the Isobath anymore but just doing a U-turn when it has finished one way or the other, and in green where the part where the robot is looking for the Isobath. So we can see that there is a stable cycle, because first it's doing what we call a reference between A and B, here in dark blue, and it's a bit hidden here, and then it does a U-turn, starts going back, and it's reaching A, but it thinks A is a little bit further. Then it's doing a U-turn. It's going here. It thinks it's on A. It's going this way to B, and it reaches B, but thinks B is right here. But then there is a stable cycle from this part and this part, and it can run indefinitely. So we have a stable cycle, which is not really the finite part, but we have something stable, so we can go to the next step, which is use one vehicle doing a stable path between 2 points, and use other vehicles to explore the area around our reference vehicle here depicted in red. And after the mission, we will process all the data. First, put the absolute position of the reference vehicle on the map. Thanks to its measurement, we know it's on the Isobath, and thanks to its measurements, we will be able to know on which part of the Isobath it is on the map. And then, as we have, thanks to acoustic communications, the relative positions of the other AUVs in the red robot frame, we'll be able to have the absolute position of the yellow robot after processing. So thank you for your attention, and if you have any questions, leave a comment on this video.